In this video, we're asked to test the convergence of the series n squared e to the negative n as n goes from 0 to infinity. And we're going to use the integral test for this. I'm not saying it's the only way to do it, but I wanted to look at the integral test to approach this thing. So to perform the integral test, we look at the integral of the related function x squared e to the negative x on the interval 1 to infinity. And if this integral converges, then we're guaranteed that the entire infinite series converges. In other words, it's got to add up to something finite. Well, this is a classic integration by parts integral, and we're going to let u equal x squared. And that means du is 2x dx. dv is the rest of the integral. That was e to the negative x dx. And that means v is negative e to the negative x. Now we apply the integration by parts formula, and that starts with a u times v. So negative x squared e to the negative x. That's evaluated from 1 to infinity. Minus the integral of v du. And v is carrying a minus sign here. So we're going to pull that in front of the integral and cancel that minus sign. And I'm left with the integral of 2x e to the negative x dx. And things have gotten simpler here. The integral that we're left with only has x to the first power in it because we chose that original substitution u equals x squared. So that integral is a little bit better because we knocked down the power of x. We are going to have to apply integration by parts one more time to knock that power of x down again. Before we do that, I want to evaluate this first piece of the expression. And the lower limit is not a big deal there. If I sub in x equals 1, I get a negative 1 out in front and an e to the negative 1, so not a big deal. But subbing in the infinity is a little bit tricky. And the issue there is that I end up with an indeterminate form. If I sub in infinity for x, I get an infinity squared e to the negative infinity. Well, e to the negative infinity is 1 over e to the infinity, or 0. So this is an infinity times 0 indeterminate form. So we need to be a little more formal about it, and we're going to re-express this as a limit. The limit as x goes to infinity, negative x squared e to the negative x. Again, that's an infinity times 0 indeterminate form. And what we want to do is re-express this as a fraction and then apply L'Hopital's rule. So I write it as negative x squared over e to the x. And now this thing is an infinity divided by infinity indeterminate form. I'm allowed to apply L'Hopital's rule to this. And with a little bit of experience, you see what's coming here. I differentiate the numerator and I get a negative 2x. Differentiate the denominator, it just returns an e to the x to me. And what I mean by seeing what's coming is that that denominator is never going to change, even as the power in the numerator keeps going down. So this is still an infinity over infinity indeterminate form. I apply L'Hopital's rule for the second time, and I get a negative 2 over e to the x. Now this is unambiguous. If I sub in x equals infinity, I have a constant divided by e to the infinity. A constant divided by infinity is always going to give you 0. So when I sub in the upper limit to this first piece, I'm getting 0. And then I subtract what I get when I sub in the 1 for the lower limit. Subtracting that lower limit kills the minus sign that was out in front, and I just get a 1 times e to the negative 1, or a nicer way to say that is 1 over e. I'm going to go ahead and pull the 2 out of the integral while I'm writing this step. And there we go. We have 1 over e plus twice the integral from 1 to infinity of x e to the negative x dx. We have to apply integration by parts for the second time. And I'm going to let u equal x this time. That means du is equal to dx. dv is the rest of the integral, which was the e to the negative x. dx, which means v is negative e to the negative x. Now don't forget to copy down that 1 over e. That was a spectator here. And then we have twice this integral, and we're going to apply integration by parts. And u times v is a negative x e to the negative x. We're evaluating this from 1 to infinity. And then I have minus the integral of v du. And again, the v is carrying a minus sign, and I can pull that in front. And now I just have the integral from 1 to infinity e to the negative x dx. And I'll go ahead and just compute that integral before we worry about evaluating across the limits of integration. All I do is guess the antiderivative, which is negative e to the negative x. And I'm evaluating from 1 to infinity. Now when I sub in the infinity in this second term, the result is unambiguous. That's e to the negative infinity, or 1 over e to the infinity. I'm going to get 0 out of that. But the upper limit in the first term, when I sub in that infinity, I'm stuck in the same situation where I get an indeterminate form, infinity times 0. So I need to do a little side note to compute that using L'Hopital's rule. I'm going to go ahead and streamline it a little bit this time and immediately write it as a negative x over e to the x. That's an infinity over infinity indeterminate form. I apply L'Hopital's rule and get a negative 1 over e to the x. This unambiguously goes to 0 as x goes to infinity. So that upper limit vanishes. So getting back to our expression for the original integral, I have a 1 over e plus a 2. And then in my first chunk here, my upper limit vanished, and then I subtract what I get when I sub in the lower limit. Well, the subtraction is going to kill the minus sign that was out in front. So I get an x e to the negative x where x is 1. That's a 1 e to the negative 1, or a 1 over e. In the second piece, again, the upper limit vanished. I subtract what I get in the lower limit, giving me a positive sign. And what I get in the lower limit is just e to the negative 1, or 1 over e. Now in those parentheses, I have a 1 over e plus 1 over e, which is 2 over e. And then I'm multiplying it by 2, which gives me 4 over e. I add that to the 1 over e out in front, and I get a 5 over e. And the whole point with the integral test, again, is that if this integral converges to some finite number, it guarantees the series itself converges to some finite number. So this is really the end of the argument. I showed that the integral converged. Therefore, the series itself converges as well, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.